Assalamu alaikum. Today we are doing experiment number 6, conservation of energy, law of conservation of energy. I'm sure everybody know about the law of conservation of energy. Maybe from grade 7 you start to hear about law of conservation of energy. Yeah, energy can neither be created nor be destroyed, but we can transfer one type of energy into another type. So that means in fact, what it says, we cannot create or destroy energy. That means we are not able to create or destroy energy. What we can do, we can only transfer one type of energy into another type, right? That is the idea. And today we are going to discuss about that in this experiment. So the objective is to verify law of conservation of energy. Our experimental objective is to verify verify law of conservation of energy, So that is objective. In fact, we know that, the total mechanical energy of the system is a constant. That means that delta E is going to be 0, or, the change in, the total energy is going to be 0. That means the total energy becomes constant. That means kinetic energy plus potential energy is a constant, right? So that is what we are going to do in this experiment. In fact, in our experiment, we have a spring, a spring, and we're going to compress this spring. We're going to work on the spring. You are going to do work on the spring. If you do work, your work is going to store in the spring as potential energy, and that potential energy stored is half k x square. You don't know what is k, you don't know what is x. Definitely some of you know, but I will explain that. Then the energy stored in the spring, half k x square, will be equal to what? In fact, if I ask you, the spring stored energy, from where it get energy? I said I compressed. That means the energy transferred into the spring from me. That means I did work on the spring. So my work is stored in the spring as elastic potential energy. So it is actually a transfer of energy, because my energy, the energy that I gain from the food, right, the muscle energy, I compress here. So it is transferred now here as potential energy. And the energy that I transfer, actually I transfer the energy, right? So that energy is now here as potential energy. So there is a transfer happen. So in fact, if I can ask you, from where I get energy? Yes, I get energy from food. Okay, food means, yeah, food, from where food get, yeah, you know that it is all a kind of a transfer. No worry about that now. So let me conclude that. So the energy transfer is now in the spring, it is stored there. In our experiment setup, actually, we have a frictionless track. So here, I'm going to keep a cart of having mass m. Okay, and imagine when I compress this spring, the spring stored some energy. Let's say the spring stored, let's say 10 joule energy. So that this 10 joule energy, from where it stored here? From my energy. Now this 10 joule energy is there. The moment I leave this, actually I am holding this with my hand. The moment I leave my hand from here, immediately the car will be moved or accelerated. That means it will have a velocity. It will be moving with a constant velocity because it is a frictionless track. So it will be moving with a speed. Let's say the velocity that it attained during this time of force is, let's say, v, then it is going to have an energy associated with this moving body. Everybody know that that energy is called kinetic energy, and that is equal to half mv square. So the kinetic energy we can calculate because I know the mass of this, or if I don't know, I have a lab, mass I can balance, so I can easily measure the mass. And also we have a photo gate or a motion detector here. By the help of the motion detector, I can measure its velocity. So that means I can easily calculate the kinetic energy. So if I calculate the kinetic energy according to the rule, because we cannot create or destroy energy, that means here there is no other forms of loss of energy. That means this kinetic energy also must be equal to what? 10 joule. If these two are equal, means if these two are equal, if you do the experiment and if you see that both of them are equal, means we can say we verify law of conservation of energy. So that is our today's plan. So what is our plan today? We are going to calculate the potential energy stored in the spring. Also, when the potential energy is transferred to the cart as kinetic energy, we will calculate that kinetic energy, or we will measure that kinetic energy. Then if we see that both the potential energy and kinetic energy are equal, means we will say we verify the law of conservation of energy. So that is our plan today. Now, to do this experiment, I said about the experiment and the experiment plan and objective of the experiment and the summary of the theory. Now, yeah, there are few questions. It is based on the law of conservation of energy. Then if you move, there is a data analysis part. And if you look into the data analysis, firstly, I'm talking about the spring constant because I want the spring constant Y, and I will teach you all that. Then there is a graph here. I'm asking you to plot the F versus X graph, F force and X the displacement in the spring graph. I will explain you all that, then you will understand. Then there is another page for the kinetic energy calculations. That means here we will get the potential energy. Then here from the second part, I'm going to calculate the kinetic energy. Then if these two are equal, we will say we verify the law of conservation of energy. That is our plan. Now, before I move into the experimental setup, let me just solve these problems. Okay, the sample exercise. I told you that these are the sample exercise, and some of these questions will be coming into the final exam. So be careful. Now, the first question, let us do it. According to the scientific definition of work, pushing on a rock accomplishes no work unless there is, yeah, according to the equation, work equal to force times displacement. If you push on a rock and if the rock is not displaced, so the work done will be what? Because if the D is 0, the work done will be 0. So what is the right choice? Is an applied force greater than its work? No. A net force greater than 0? No. An opposing force? No. A movement in the same direction as the force. If there is no movement in the direction of force, then we will say there is no work. So that is the right answer. The metric unit of joule is a unit of, yes, we know that the unit of work, because work, energy, all have same unit we call joule, right? Because energy is the capacity to do work. So energy and work will have the same unit, and it is joule. And there are so many forms of energy. Potential energy, yeah, unit is joule. Work, unit is joule. Kinetic energy, it is a work, it is unit of joule. So which is the right answer? Yes, all of the above will be the right answer. So this is the right answer. So these are units. Now let's move to the third question. All of you please read it and try to answer. The potential energy of a box on a shelf related to the floor is a measure of the potential energy of a box on a shelf. That means this is the floor related to the floor, right? And this is a shelf, and on the top of the shelf there is an object. Okay, then we know that the potential energy is stored here. The gravitational potential energy is mgh. If the mass is m and if it is at a height h, the energy stored is the gravitational potential energy, and it is called mgh. Now let us read this question. The potential energy of a box on a shelf related to the floor is a measure of the work done putting the box on the shelf from the floor. What is the work done for me to keep this object? Imagine if the shelf was if the object was here, if I raise this all the way up and put here, how much work I did? Yeah, the work done is actually the force is mg and it goes to a height h, so force into distance, so mgh is the work done, and that work done is stored as the potential energy. So this is a correct choice. Okay, the work done putting the box on the shelf from the board. This is a correct choice. Let's look other one. The weight of the box times the distance above the floor. This is again, weight is mg times h. Oh, that is again a choice, correct. The energy the box has because of its position, yes, because of this height, the position h, the energy, if the h is 0, the energy with respect to the floor is 0. So any of these or all of these is a measure of the potential energy stored. So in fact, the energy the box has because of its position above the floor. The energy the box has because of its position above the floor. Yes, all these are a measure of potential energy, right? Now I hope everybody understand. Now let's move to the fourth question. Please read it. Which quantity has the greatest influence on the amount of kinetic energy that a large truck has while moving down the highway? Here we know that the kinetic energy is given by half mv square. Here, which one will have a large influence, they are asking. Imagine if the mass of the object, imagine if the mass is 2, I just doubled from mass 2 to 4. So, but imagine if I'm going to have a velocity 2, I doubled the velocity from v2 to 4. So which one will have? Because in the kinetic energy equation, we know that the mass and velocity is related. So I am going to look into these two cases. So if I increase the mass from 2 to 4, what will happen? Keep the velocity same. Or if I increase the by keeping the mass same, but I increase the velocity from 2 to 4, double, which one will? Let's have a look. The kinetic energy in this equation, imagine if I'm not going to change the velocity. Let's say first try with the mass. Imagine if the mass is 2. So it is half into 2 into v square. It is 1 v square or v square. So if I increase the mass, okay, and let's say the velocity, okay, now if I increase the mass from 2 to 4, what will happen? It becomes half into 4 into v square. So it will be 4 by 2, 2v square. That means this is the kinetic energy. The kinetic energy now, it is the previous kinetic energy is v square. The new kinetic energy is 2v square. That means it doubled. The kinetic energy doubled here. Now look at this case. We're going to change the velocity. Half m v square. V is 2 to 2 square. So the kinetic energy is here 2 square is 4. 4m divided by 2. So 2m is the kinetic energy. Now if I increase this kinetic energy from, sorry, the velocity from 2 to 4, what will happen? 4 square. So half into m into 4 square is 16. So it will be 8m. How much is the kinetic energy increase? From 2m to 8m. So the kinetic energy increase 4 times. Here 2 times. So which one will have more impact on the kinetic energy? Is it the mass or the velocity? So the answer is very clear, not mass, it is velocity. So we discard these two, right? So the answer is C. So the C, the velocity has a big impact. Now let's move into the second question. The fifth question. The law of conservation of energy is a statement that everybody know that energy can neither be created nor be destroyed. Energy must be conserved. Yeah, the total energy of a system is a constant. And you are breaking a law if you waste energy. Eh? If you waste energy, you are not breaking any law, so it is wrong. The supply of energy is limited, so we must conserve. That is true, but it is not the conservation of energy statement. Law of conservation, the total amount of energy is a constant. The total amount of energy is a constant. Yes, the total energy of a system is a constant. Energy cannot be used to faster than it. So all these are wrong answers. So our correct answer is C. Energy is the ability to do work. The work need to create a potential energy. Oh, yes, we need to do work in order to store potential energy or kinetic energy. The work that can be done by an object with the potential energy or kinetic energy, we can do work. So all these are energy. Yeah, so that is the right choice. All of the above. Am I right? Because this is the same thing I said during all this time, right? So the all of the above, right? So that is the right choice. Now, I think you understand all these questions. All of you, please you need to understand this, because based on this, we are going to bring questions in the exam. So be careful. If you have any doubt, you can look into this once again. Then you will understand. It's already explained, right? Now, I said, yeah, you need to know how we are going to do this experiment. That's part I will explain you now. So let's move into the explanation of, first of all, I need to introduce you what is K, spring constant. In our experiment, I said I'm using a spring. I'm using a spring, right? I'm using a spring. So if it is a spring, okay, actually in our experimental setup, because you're going to watch the video, right? In this video, you can see I am using a spring like this, it's a hoop spring, okay? You will see that in the video. So this is a spring. I mean, of course, it's a spring. Why I call it spring? Because you know what is the property of a spring. If you compress, imagine if the spring, if you compress or if you elongate, imagine you are going to apply force in this direction or this direction. This is now the spring is in the equilibrium position. The spring will move compressed or the spring will elongate. So that means the spring will move from the equilibrium position. So this is the equilibrium position. So x equal to 0 to this x or to this point. So this is the elongation and here is the compression of the spring. Yeah, you know that. Like every other spring, this is a normal spring, you know. It is very common for you, right? Imagine if this is the spring. I mean, if I apply a force here, imagine if I'm going to hang a mass here, or if I push this direction, if I, if I pull this direction, okay, this will be moving. It will be, that the spring, imagine if this is the equilibrium position, x equal to 0, that means it is an equilibrium, there is no movement. But if I apply a force here in this direction, what happens? The spring will be elongated. So let me show you that. The spring is elongated, and very bad drawing, no worries. Okay, now the spring is like this. So how much it extended from this equilibrium position? Now the spring is extended to a distance which is we call x. And actually, you notice that why the spring extended? Because I applied a force in this direction. So can I ask you a question? If I increase this force, what will happen? What will happen? What will happen if I increase this F? Of course, your answer is correct. The X will increase. The F, as if I increase F, the X will increase. Or you can say F is directly proportional to X. Why? Because as I increase the force, the extension produced the spring is increasing. It's the same thing. As I compress the spring, the extension produce, the compression in the spring also increase. This is the same thing. The spring, maybe you can compress also. Imagine if the spring is in this situation and you have a mass attached, you just push this. So it will be compressed, right? And this is the distance it compressed. And actually, when we talk here, we need to talk about a little bit about, I need to talk a little bit about Hooke's law. What is Hooke's law says? Within the elastic limit, within the elastic limit. Why this? This is a condition within the elastic limit. What is the meaning of elastic limit? I said here, if I increase the force, the extension is going to increase. Is it true for all like force? You know that if I apply force more and more and more, what will happen? The spring will extend and no, the spring will break. So this property only exists in a certain limit of force. So there is a range. I cannot apply too much force on this. So within that force, or within the elasticity, because actually if I increase more force, if I apply more force, the spring will damage. Then then this will not be a spring. It will be a piece of metal then, right? A metal wire. So there it will never show the property of a spring. Yeah, so that's why I said this is only happening. This F is proportional to X only within the limit of elastic. Within the elastic limit, F is proportional to X. And one more thing, what F here? In fact, the moment when I apply force, there is a force developed in the spring. What force? The spring, because the force that you are applying is called the deforming force. Why we call it deforming force? Because I apply a force to this spring and the spring shape is changed, so deform it. So that's what we call the deforming force. But you know that even though the spring shape is deformed, the moment you remove your force, the spring will go back to its original condition, its equilibrium condition, its normal condition. Why? Since there is a force inside the spring, we call that force is called restoring force. The force in the spring, the natural force in the spring due to their molecules or the material or the geometry of the spring, we call it restoring force, right? So what happens here? We know that the deforming force and the restoring force are equal, but they are at opposite. Now look at this. We are talking about the restoring force. Here the restoring force and the deforming force are equal in magnitude, but within the elastic limit. But the restoring force, imagine if the deforming force is in this direction, the restoring force will be in this direction, in the spring. So look at the spring, the restoring force and the extension produced. Here the extension is in this direction. So are they in the same direction? No. So we can say that this F is directly proportional to minus X. And actually we know that this is true for all spring irrespective of the hardness of the spring, because you know that the springs are available with a different size, different hardness, because the spring that we use in our car, airplane, train, all are very strong pin and strong spring. Also you use springs in your pen, right? In your pen, most in your watch. All these are very light spring. Okay, the lightness or hardness of a spring is given in terms of this constant. That is what we call the spring constant. So F is directly proportional to X and F is equal to minus Kx, where K is a constant called spring constant. Where K is a constant. So for the simplicity, we are not going to bother about the direction of restoring force and K. We're just going to simply take on this equation as F is equal to Kx. So we understand that the force on the spring is, if you increase the force on the spring, the extension is also increasing, or the compression is also increasing. So we can say F is directly proportional to X, or F is equal to Kx, where K is a constant we call spring constant. And you understand that for all spring, for every spring, this is true. As you increase the force, the extension or the compression will increase, whether it is a light spring or a hard spring or a heavy spring. This is true. So this is true for all the spring. Then here comes the new thing that we call the constant K. So K equal to F divided by X. So that means if K is big, if the K value is big, means imagine K is 800. Yeah, what is a unit? Newton per meter. Oh, K is 800 Newton per meter. That means this is a heavy spring. Maybe K can be 2 Newton per meter. So that means it's a, or maybe less, K can be 0.02 meter, Newton per meter. So these are light spring, these are heavy spring. Anyway, our today's experiment, we need to first calculate the spring constant of the system or the spring that we are using. For that, I'm just going to show you how will I do that. So very simple. In our experimental setup, what I am going to do, first of all, I have a spring. So here I'm going to apply a force with the help of, I can just simply apply force, and there is a force sensor here. So this force sensor will record the value that I applied. And of course, when I apply the force, the spring is going to compress at distance X. So right now I know the force, I know the value of X. Next, what I will do, I will increase this force from F to F1 or F2. I have a new force. Of course, because of that, this X is now a new value. So I have another X2. Right now, I have a set of F1, F2, F3, X1, X2, X3. If I have a set of values, and we know that in the equation F is proportional to X, so F is equal to a constant into X. That means these are linearly proportional. That means if I have a value of F, if I plot F along the y-axis and X along the x-axis, it is going to be a straight line. And you understand that the slope is what? The slope equal to y. Y value is F divided by X. F divided by X from this equation. What is F divided by X? It is a spring constant. Okay, it is a spring constant K. So I'm going to get the spring constant from F versus X graph. So that is the first part we are going to do here. You look here. I'm going to compress the spring for a distance of 1 centimeter, 2 centimeter, 3 centimeter. Then I will find the spring constant. Then you will understand what I am going to do. Please watch the recorded video in the lab. Then we will continue the data analysis after you watch the video, So that's all for the introduction part. Now you watch.
Assalamu alaikum. So today we are going to verify law of conservation of energy. So the objective of today's experiment is conservation of energy. We are going to verify. So in order to verify law of conservation of energy, we have this equipments. So here you can see there is a spring, right? And what I am going to do, I'm going to transfer some energy into the spring. See how I am doing? I'm just compressing this spring. So look at this. When I compress the spring is storing energy. We call it elastic potential energy. And you can see that the moment I leave my hand, the spring transferred that energy into this card as kinetic energy. If we can calculate this potential energy and this kinetic energy, definitely this two will be equal. That means if these two are equal, means we can say we verify law of conservation of energy. So this is our today's experimental objective. In order to do this, in order to verify law of conservation of energy, the first thing I need to understand what is the energy stored in this spring. We know that the energy stored in the spring is elastic potential energy. So the first thing, in order to get this potential energy, we know the equation for elastic potential energy is half kx square, where k is the spring constant and x is the distance we compress the spring. So if I can get the spring constant, then definitely I can calculate the potential energy here. And at the same time, we have a motion detector. While this moves, the motion detector can provide us its velocity. We already know its mass. So that means the kinetic energy is half mv square. So we can easily calculate the potential energy and kinetic energy. Definitely these two will be equal within the limit of error. So that is our today's plan. Yeah. Now we are going to find the spring constant of this spring. In order to find the spring constant, our plan is we are going to get a set of displacement for, we are going to displace this spring for a set of, displacements like compressing this for 0, 1 centimeter, 2 centimeter and 3 centimeter. While we compress the spring, we can see that this force sensor attached to this will read the force, corresponding force there, and it will be displaced here, and we can get the graph of force versus displacement, and we are going to do that. Now look at the picture. You can see that we compress this to a displacement of 0 and the corresponding force is 0. I'm going to collect that data. I just click the collect data, and now I'm going to keep that value. See, when I press this keep button, I can keep that value of the force. I'm going to keep that value of the force. And that force is 0.003 Newton, and the displacement is, I'm going to enter here, I enter the displacement is 0. So you can see here the displacement is 0. I'm going to put OK. Now the system is running, and we are going to compress this spring to another 1 centimeter. Now you can see, while she is compressing this to 1 centimeter, you can see that the force is now 0.996. So I'm going to keep that value of force by pressing this button. When I press that, that force is stored there, and I'm going to enter the corresponding displacement, that is 0.01, because 1 centimeter in meter, right? So I'm going to take the second reading. You can see here I have two readings now. For 0, the force is this. For 1 centimeter, the force is this. Now I am going to compress it further, and definitely the force will increase. Now we compress this to another displacement, and it is, I'm going to keep that value. See the value, it is 1.6 or 1.6. I'm going to keep that value. You see, I just kept that value, and I'm going to enter the corresponding displacement. It is 0.02 meter, or that means 2 centimeter. Now I have 3 readings, and I'm going to take the last reading. I'm going to compress it further for 1 centimeter. That means 0.03 meter. So the force in that is, let it be exactly 3 centimeter. So I'm going to keep that value, and now I'm going to get that it is 0.03. That force I just took, and I'm going to enter that value. Now I'm going to stop my data collection. When I stop data collection, I can see the values here. It is in a small scale, so I'm going to auto scale it. While I auto scale, I'm supposed to get a straight line, but it is okay. We have a small bend here. Now you see, I'm going to find the slope of this line. The slope of the line will definitely represent the spring constant. Now we can see that the spring constant is 78.98. That means the slope represents, slope is K, spring constant, and the spring constant is 78.98 Newton per meter. So right now we have the spring constant, and for the further, actually, what is our plan? Our plan, right now we have the spring constant. What is our plan? Our plan to find the potential energy. We know that potential energy is half K x square. Imagine if I compress this spring for only just 2 centimeter. If I compress this to 2 centimeter, I can definitely calculate the potential energy. What is the potential energy? Half into 78.98 times 0.02 square. So I will get the potential energy in joule, and the same potential energy I can get by selecting the area under the curve up to this displacement. So I select this area, and we have an option here. We can integrate the function over the limit 0 to 2, and definitely the area under the graph represents the area under the graph represents the area under the graph. This is the integration option, and I'm going to integrate it over that. And here I am getting the area under the graph. It is shaded, and the area is 0.0179 meter Newton or Newton meter, whatever it is. So the potential energy we get from the graph area, it is 0.01791 joule, and definitely these two will be the same. So imagine if you wanted to do further, we can maybe take the better value. That means here I am going to get two values of potential energy. So you can get the average potential energy average. It is this potential energy P1 plus this potential energy, I call it P2 ala 2. So we will get a good potential energy. And that is the potential energy stored in the spring while I compress it to a distance or a displacement of 2 centimeter. Right now, my part is to get the kinetic energy stored in, the kinetic energy is transferred to the spring. I need to understand. So I need to open another setup, and I'm going to show you that while, imagine if I'm going to compress this, okay, see, I'm compressing this to 2 centimeter, then I'm leaving it, it start to move. So while it start to move, the velocity time graph will provide us the velocity, and if I know the velocity, I can calculate the kinetic. Find the kinetic energy of this card. In order to get the kinetic energy, I need to get the velocity of this. To get the velocity, right now, I have a motion detector here, and the motion detector will provide us a velocity time graph. And what we are going to do, we are going to compress this card exactly 2 centimeter. And we compress it exactly 2 centimeter. Right now, I'm going to run it. So can you make it? Can you compress this exactly 2 centimeter? Okay. Now the cart is compressed exactly 2 centimeter, and I'm going to start to collect data. Now we get this, and look at this graph. It is the velocity time graph, and we can see that the velocity is uniform. And of course, this is some jerks in the track, but no problem. You see, during this time, the cart is at rest. Suddenly, the cart reaches to a velocity of this, and we can see that it is going like this. You see, so I'm going to shade this area. I'm going to find the area. This is the maximum velocity. I'm going to find the statistics of this selected area. So I have an option here. If I see the statistics, that means I can get the minimum, maximum. From this, look at the value of the velocity here. It is 0.2319. So the velocity from the graph is 0.2319 meter per second. See, right now we know the kinetic energy is half mv square. So here we know the mass of this cart is 0.5 kilogram. That means 500 gram. If you substitute here, you will get the kinetic energy. Definitely the kinetic energy we calculated is very much close to the value of potential energy we calculated. If we see that both of these are equal, means we can say that we verify the law of conservation of energy. That's it.
Okay, now let's begin the data analysis. So you can see this is the graph. Maybe you notice that the graph in the video, it was with the red color. Anyway, it was actually in red color, but I just, take the print out in a black, in a black printer. That's in a black and white printer, then it's a scanned copy. Anyway, in this graph, as I explained in the video, in this graph, I am plotting the force along the y-axis and the displacement along the x-axis. So it is a F versus X graph. And you understand that the F versus X, this is the line, and this is a line, it's a straight line, and we fit this into a straight line relation, and that is the equation of the straight line. Y equal to mx plus c. In this, m is the slope, so the slope represents k. So here the slope is equal to k. What is k? Yeah, 94.24 Newton per meter. So you understand that this is the spring constant K. The spring constant of the spring that we used in the lab is 94.24. So that's the first goal of us. And in the second goal, actually, here I just calculate the area under the graph by using the integral function. You maybe notice that I just said in the video integral function, because if I am going to integrate the work done, integral fx dx from 0 to 2, it will be half kx square, right? And actually that is this. The energy stored in the spring, it is a potential energy. So that's why I integrate the function from the limit 0 to 2. And when I integrate the area under the graph, actually the area under the graph represents the potential energy. How? It's very simple. Maybe you notice that. I can maybe just explain you this. Look here. Look at this area. The area is the shaded area. Imagine if this is the shaded area. The shape of the shaded area is a triangle. And we know that the area under the graph represents, what is the area? Yeah, the area of a triangle. So this is, we know that the area of a triangle is half base times height. Here, what is the base? Here the base. The base represents the displacement or the distance x. And the height represents what? The force. And we know that the force is kx. So what is the base? Yeah, half x times the height. Height is f. So kx. So half kx square. So the area under the graph represents half kx square. So it is the potential energy. And actually, by the help of the computer program, we have calculated that. And that is this. The potential energy from the computer program is 0.01920. So you understand, this is already explained in the video, but now that I just make you more clear about this now. So we have taken the value, the measurement, yeah, for the force sensor. When the displacement is at 0, the force sensor reads 0. And when we displace this to a 1 centimeter, then it is 0.976, 2 centimeter, 3 cent. So these are the data we can write now in our report. So this is the report we are going to fill now. See, I'm going to show you these values here so that we can just complete our calculations. Okay, let us fill it. Okay, let us fill. Okay, now I have the first point. So all of you look, the first trial, when the spring is, let me delete this. Okay, yeah, the first trial, let me use a color, different color. Okay, this color, fine. The first trial, the displacement is 0, so the force sensor reads 0, so we are not going to calculate this, just put blank. Now for the second point, from the table you can see that when I displace this to 1 centimeter, the force is 0.976. The force is 0.976. If you want to see, I can show you a little bit enlarged. 0.976. The next one is 1.879, then 2.840 for 2 centimeter, and 3 centimeter 2.840. So you can see that, right? I'm going to write that, and of course you will cross check this with the data that you have right now, right? So let me complete this. Okay, so for 2 centimeter it is 1.879, and for 2 centimeter the force sensor read 2.840. Now I'm asking you to complete this. The spring constant, yeah, spring constant is delta F divided by delta X. So this is delta F, 0.976 minus 0 divided by 0.01 minus 0. That means, in fact, 0.976 divided by 0.01, right? So I can just directly write. I don't want to show you this. It is very simple. Delta F means, in fact, this divided by this divided by this. So in fact, if you wanted to get, just to divide this by, this is the F and this is the X. So you just divide F by X, you will get the delta F. I'm going to just complete it now quickly. So tell me the first one is 0.976 divided by 0.01. So it will be 97.6. The next one is 1.879 divided by 1.879 divided by zero point zero 0.02. It will be 93.95. Let me use a different color. Okay, 93.95. You understand what I am doing? Okay, next thing. What is this? 2.840. Yeah, 2.840 divided by zero point zero 0.03. I'm getting 94.66. So I have all the spring constants. But everything is very close, right? 97. No worries. Just it's for the calculation. We can calculate the potential energy stored when you compress it to a 2 centimeter. It is half kx square, half into k, 97.6 into zero point zero 0.01 square. Here, what is the value? 0.5 times 97.6 times 0.01 square. I'm getting the potential energy is 0.00488. Here I will calculate the potential energy. Same way, half into 93.95 times 0.02 square. So it is 0.01879. And this is the one we will use it for today because we calculated the potential energy for 2 centimeter compressed. Because you remember in the video I said we are going to do the experiment by compressing the spring for 2 centimeter. That's this reading. When we did the calculation, we get this, right? Or we can do in many ways. Anyway, next thing, what is the kinetic energy stored, potential energy stored? It is 0.5 half into K 94.66 into 0.03 square. So what you notice that as I compress it more and more, the potential energy storing is going to be more. So that is true. You look at the potential energy in this 0. Yeah, here it is 0.04. It is 0.08. Yeah, so that's what we notice here. As we increase the compressed length, the potential energy stored in the spring is also increasing. So now let us look here. Plot F versus X. Show the rough graph here. Attach a printed copy along with the report. What will be the slope? What will be the area under the graph represents? Show your work on the graph. In actually, we already did the graph of F versus X. That is this. So you don't need to do another extra graph. This is the graph we plot, right? So this is the graph by the help of the computer program we plot, and we are going to attach it here. So this is the graph we plot, and from this actually you can read now, right? From this, all this we already read it before, right? Actually, so from this, yeah, what will be the area under the area under the graph represents? What will be the slope? The slope is K, and the slope equal to what? We get 94.24. Then what we are asking, what is the unit? Yeah, Newton meter. What is the next thing? What is the area under the graph? Yes, the area under the graph represents what? The potential energy, and that is equal to, from the integral function, that potential energy from the integral function, it is, we calculated, it is not calculated, we did in the print out, it is 0.01920 Newton meter, or we call it joule. Look at this. Maybe if I show you here, it will be bigger in size, so that's why. What is the, yeah, 0.1920 joule, right? So I just wrote that value here. Okay, everybody. Now, yeah, show your work on the graph. We did it. Now let's move to here. Slope of the line. Yeah, that's what I did here, right? So Here I am asking you to draw a rough graph of forces X. So you understand that the K is 94.24. Then the spring constant, yeah, the slope will be 94.24. The slope will represents the spring constant. So same thing. What will be the area under the graph? Find the area under the graph for the compressed length using the integral function. We did that using the integral function. That value is 0.01920. That is the first thing. Now the elastic potential energy is stored in the spring. You can maybe, here I just use that technique. You see, I have the potential energy for 2 centimeter compressed length. One is this, and another one from this. What is that? 0.1879. 0.1879. So I have two values, 0.1829. Or so I have two values. I can take the average of this. So you just finally you write that value. You know, this is the final value. So it will be 0.1920 plus 0.1829 divided by 2. When you add, you will get 0.01875 joule. So this is the mean value. So we calculate the potential energy stored in the spring. We know that according to the law of conservation of energy, this potential energy, whatever it is, must transfer to the cart as kinetic energy. That's what the second part. Here, using the logarithm program, find the kinetic energy. That is the verification of conservation of energy. That is the second part. Let me move this to the second page so that it will look nice. Okay, so this is the second page. Here, using the logarithm program, find the velocity of the glider in the frictional attraction, the stored elastic potential energy for a compressed length of 0.0 transfer to the glider. VT graph. So I have the velocity time graph. So that means just the computer is giving me the velocity time graph because the cart was initially rest, then it moves to a velocity, and that is the velocity. So how much is this velocity? We did the experiment, and let's see the value of the velocity from the graph. So this is the graph. This is the graph, and from this, that velocity is the maximum value. That is the mean value of the maximum is 0.2639 meter per second is the velocity. And we know that the mass of the glider is 500 gram or 0.5 kilogram, right? So from here we can calculate the kinetic energy, half m v square. So let us do that, you see. So half mv square. So that means I have now the velocity, that is 0.2639. Let me write it here so that we can complete the report. Maximum velocity 0.2639. What is the mass of the glider? 500 gram. So what is the kinetic energy? Just simply calculate half mv square, half mv square, half into 0.2639 square. When I did the calculation, I'm getting 0.0174. The kinetic energy was the potential energy was 0.018, and this is 17. Are they very close? Yes, they are definitely very close. That means the compare both elastic potential. Are they equal? They are not equal, but they are very close. They are equal within the limit of error. They are equal or very close. They are very close, right? And if not, why? Yeah, why they are not equal? Because of course, when the cart roll through the track, you know, we hear sound. That means there is a loss of energy as heat, sound, etc. That's why it is not exactly equal, but within the error of these limits of error, it is very correct, or it is very close. That means we can say the potential energy 0.018 is almost equal to the kinetic energy 0.0174. So are they close? Yes. So within the limit of error, we verify now the law of conservation of energy. So actually, I believe now you understand this. So that's the only thing we did in this experiment. So let me conclude now the experiment. Have a look once again. We calculated the potential energy from the graph, or we have many ways to calculate, right? So first of all, let me go back to everything and I will conclude now. Okay, fine. So our experimental objective is to verify law of conservation of energy. So that means in this case, the total energy here, we understand that the potential energy is transferred as kinetic energy, and our idea is to look for the potential energy. And today, when we calculate the potential energy is 0.18, and it is transferred as 0.0174. There is a slight difference. It could be due to our experimental, you know, error, because when we do experiment, definitely there will be loss. Maybe we don't compress it exactly to 0.02. Maybe there is a loss of energy in the form of sound, heat, because the spring, when we compress the spring, there is the internal energies formed there, right? So there is the heat, and so many ways of loss of energies are there. So that could be the reason. So our objective is to verify law of conservation of energy. We did that, and for that we use this theory, right? What is the theory? Yeah, the theory I'm going to conclude you once again. When we plot F versus X, we get the spring constant K. From the spring constant K, I calculate the potential energy stored when we compress the spring to 2 centimeters. This is the value we choose, right? So that's why the half K value we know, the X value is this. So half K square, we calculate the potential energy. Now, by the help of, then we solve this, right? Now, from this we calculate the potential energy by the help of the velocity time graph. We calculate we know the velocity. From the velocity, we calculate the kinetic energy, and that is very close to the potential energy. So we verify the law of conservation of energy, right? Now, in the exams, we usually ask questions like this. Maybe we will give a figure like this. And if I show you this, you need to understand the idea. This is the area under the graph, and the unit you look, it is a joule. So this represents potential energy. And if I show you this represents what? Spring constant K. So if you know the spring constant, and if I say that it is, instead of 2, if I say it is 3 centimeter, you will just calculate the potential energy, because half K X square. If I don't show you this, still you can calculate the potential energy. You should be aware about this, okay? And this is the velocity time graph. Here we get the maximum velocity, that is this, right? Then we calculate the kinetic energy, and everybody know the equation for kinetic energy is half mv square. So we calculated that. Now this one, the the trials, I have 4 trials. The first trial, I compress this to 1 centimeter, that is in meter this. Then 2 centimeter, the corresponding force. 3 centimeter, the corresponding force. Then I just calculate the kinetic energy, sorry, the potential energy stored. Here I just put blank because, no compression, so no potential energy stored. Now this is all we just explained, right? So I believe everybody, it is clear now, right? So I'm done with this experiment. Now, this is our 6th experiment, right? Now we will do another 2 more experiments, and the next experiment is going to be based on, based on momentum. Okay, I will explain you that inshallah next week.